Today I want to talk about what happens to excess charges when they're in or on a conductor. We talked in Physics 20 about a term called equilibrium, and you probably saw that term in Science 10 as well, or certainly in chemistry or biology as well. We said equilibrium means balance, right? Equilibrium means balance. In Physics 20, we said static equilibrium means that something is in balance and not moving. So at rest and not moving. The goal when we have excess charges, excess electrons in or on a conductor is to reach a point of static equilibrium. These charges, these electrons, will constantly repel each other. And as a result of that repulsion, they're going to move around for a little while. It's just like if we have a whole bunch of extra people in a room is a little bit too crowded, then people kind of try to carve out their own space. They move around until they can reach a point of equilibrium where they're comfortable. They're repelling each other. They're pushing each other away until they reach that point of equilibrium where everything is kind of balanced and people remain at rest. That's what electrons want to do as well. But what does the distribution of the electrons look like? What does the distribution of the electrons look like once it reaches that point of equilibrium? That's what we're going to talk about today. One final note before we look at specific shapes and materials. I want to point out that I say that this doesn't occur in conductors. The electrons don't move around. Sorry, it doesn't occur in insulators, only in conductors. The electrons don't move around until they reach this point of static equilibrium. That's not quite true. We know that electrons can move around in insulators as well. They just don't move around as well or as much. So we won't necessarily get this predictable pattern with insulators as we do with conductors, where they're free to move about pretty much wherever they want. All right. The first shape we're going to look at is what we call a solid conducting sphere. This would be like a marble made out of some kind of conductor, like a metal. Or maybe it's like a pool ball, except it's made out of metal. Okay? Some kind of ball bearing. Right? It's a sphere, it's a globe, but it's made out of metal, and it's completely filled in. Right? It's not hollow at all. If we have extra charges, extra electrons, in or on this material, then they repel each other. We've got three drawn here in diagram A. Let's see these three electrons all will repel each other. Now, if we had 1,000 extra electrons, the same thing would happen, but the diagram would look much more complicated. But it would ultimately boil down to the same principles. I want to label these electrons 1, 2, and 3. And then I want to look at the forces that are acting on each of these electrons as a result of the other electrons. They start out in random places, but what happens to them? Well, if we look at charge A, or charge 1, then it's going to be pushed away by number 3. We'll call it the force of 3 on 1. Gets pushed away from it, repelled by it, up here. Now, charge 1 also gets pushed away by number 2. So we're going to say F21 is up this way. Which way is the net force acting on number 1 as a result of number 2 and number 3? If I'm pushing it up and to the right, and I'm pushing it up and to the left, the net force is which way? Straight up. Good. So we're going to draw the net force acting on this up like this. In other words, that charge gets pushed to the outside. Now let's take a look at charge 2. Electron 2. It gets pushed down this way away from number 1. We'll call that F12. It gets pushed this way away from number 3. We'll call that F32. Now, as a result of those two forces, which way does charge 2 get pushed? In other words, which way is the net force acting on charge 2? We got to the right. We got down and to the right. It's going to be somewhere down to the right, somewhere down in here, in the middle. In other words, as a result of those two forces acting on charge 2 also gets pushed towards the outer surface. Now let's look at charge 3. Probably predict we're going to get a similar thing here. Charge 3 is pushed away from charge 2. It's pushed away from charge 1, and the net force acting on it is going to be this way. Again, towards the outer surface. If we do 1,000 more electrons, we'd find the same thing. All 1,003 electrons would be pushed to the outer surface. That's what happens here. Okay? No, we're not saying all electrons in this material are going to get pushed to the outer surface. We're saying all excess electrons. If we have 1,000 protons and 1,000 electrons, then they're going to be evenly distributed. But if we have 1,000 protons and 1,003 electrons, then the 3 electrons will get pushed to the outer surface, and not only will they go to the outer surface like we see in diagram B here, look at the distribution of them while they're on the outer surface. What do you notice about it? What do you notice about the distribution on the outer surface? They're evenly spaced. Yeah, that's what happens when we have excess charge on a solid conducting sphere. The excess electrons will go A, to the outer surface, and B, in a way such that they're evenly distributed on the outer surface. Always. Always. Now again, you could have an electron inside here, but if you do have an electron inside here, you've got a corresponding, if you have a negative inside, you've got a corresponding positive. So it's the excess, the extra electrons that are going to the outer surface. Does that make sense? Now, these blue lines you can see in this diagram, what do you think those blue lines represent? Yeah, it's the electric field. The electric field points toward the negative producer, and it points toward the negative producer because there's a bunch of these little individual negative particles called electrons that are on the surface of this producer. So of course, we know the electric field points toward that negative producer. And they're always going to be perpendicular to the surface as well. All right, take a look at the next one. This is a solid, flat, conducting plate. Take a look at just the first diagram for now. You got 3 excess electrons here. They get pushed to the outer surface just like they did in a solid conducting sphere. But what does the distribution look like while they're on the outer surface? Well, right now, before they've reached the point of static equilibrium, in other words, before the forces are balanced, they look like this. I want to look at these forces though, okay? Let's label these. F, or object 1, object 2, object 3. We're going to say that object number 1 gets pushed away from object 2. And it also gets pushed away from object 3. Can you tell me why F31 is smaller than F21? Why did I draw that as a shorter line, as a smaller force? Yeah, Bruce? Yeah, it's further away. The charges are the same. If the charges are the same, the distance is bigger, the force will be smaller. These two forces combined, F21, F31, combined, give me a net force on charge 1. So you got a pretty big net force on charge 1 acting to the left. Now let's look at your charge 3 here. Charge 3 experiences a force caused by number 1. Charge 3 experiences a force caused by number 2. Force 2-3 is bigger than the force of 1-3 because 2 is closer. But why are both of those forces, or the combined force, I should say, the net force on charge 3, smaller than the net force on charge 1? Yep, Julian? Because charge 2 is closer to charge 1. Now let's look at the middle one. There's a force of 3 on 2 acting this way, and a force of 1 on 2 acting this way. 1 on 2 is bigger because 1 is closer than 3 is. This is the one that I really want to focus on. What happens to charge 2 as a result of charge 1 and charge 3? Which way is it going to go? Or does it just stay where it is, right?
It's going to go to the right.
It's going to go to the right because the force to the right caused by number 1 is bigger. But as it goes to the right, what happens to the value of F12? Right?
As it moves to the right, the value of F12 is going to get lower.
Good. Okay, so as it goes to the right, the value of F12 gets smaller because that distance gets bigger. But as it goes to the right, what happens to the value of F32?
It increases.
Good. It gets bigger because the value of, or the distance between 3 and 2 gets smaller. So at some point, this force that is decreasing and this force that is increasing, at some point they're going to do what? They're going to balance. That's when it's in static equilibrium, when those two forces balance. When are they going to balance? Where is this charge going to be when they balance? Sorry? Yeah, it's going to be midway between charge 1 and charge 3. In other words, our distribution is going to look more like this, right? They're spread out, again, with an even distribution. I'm not sure why, actually, they draw these kind of in from the edges. We're not going to worry too much about that, okay? We're going to focus on this distance and this distance, recognizing that that second charge is in between, that they're evenly distributed there. So what do we see in common between this flat, solid conducting plate versus that last diagram that we saw that was a solid conducting sphere? What do they have in common? Where do the charges go? In both cases, to the outside. You know what? Let's say to the outer surface. I mean, to the outside works, but we don't want to think or misunderstand that they just go, like, they go to the outside. It's like, where are they? Well, okay, this is the classroom right now. I'm going outside the classroom right now. I'm outside the classroom right now, right? They don't go outside there, right? They go to the outer surface of these, right? Why do they not go beyond? Yeah, I just walked outside the classroom, but if I was an electron on this surface or in this conductor, then I would go to the outer surface and I would stop there. Why wouldn't I continue? Why do they stay on the outer surface versus going beyond the outer surface? Like if there's a force pushing these guys outwards, these purple forces, why don't these electrons go way the heck out here? Well, the truth is they do sometimes, but not usually. Why do they usually not go beyond the outer surface?
Because the air is an insulator.
Yeah, usually we're in air, and the air is a pretty good insulator. So they conduct through this solid conducting sphere or through this solid conducting plate until they get to the outer surface, but then they don't go anywhere further because they're limited by the lack of conductivity in the material that's around there. Now, if it was damp outside, if the humidity was high, then they would be more likely to leave the surface, right? They would be more likely to arc from the surface into the air. That's why we said when we used the static ball that day, if it's humid outside, static ball doesn't work as well because the electrons will tend to leave the static ball, the Van de Graaff, okay, as a result of the conductivity of the air. Okay? Let's assume, though, that we got nice dry air, poor conductivity, and insulator. They're going to stay not on the outside, but on the outer surface. Okay? Okay, let's take a look at another one. Oh, this one looks ugly. It's not as bad as it looks, actually. Take a look at the first diagram here. This is an irregularly shaped solid conducting object. In other words, it's more pointy, right? It's not this nice round thing. It's more pointy. It's not sharp, but we could make it sharp. Okay, the same analysis would apply if it was sharp because it would be irregularly shaped. What does the charge distribution end up looking like here? Well, let's take a look at diagram A. I'm going to draw a couple things on diagram A. Kind of transition it from diagram A to diagram B here. And I want to look at just three of the charges. The same analysis would apply if I had that fourth charge or if I had 50 charges, but we only need the 3 to show you what I want to show you. Let's label them. 1, 2, and 3. Now let's look at the individual forces now. The force of 1 on 2 is this way. Would you agree with that? Does that make sense? 2 gets pushed away from number 1. Now the force of 3 on 2 is this way. Right? 2 gets pushed away from number 3. You agree with that? All right. Well, F32 can actually be broken down into an X component and a Y component of F32. The excess charges in this irregularly shaped object will also go to the outer surface. Why? Forget about what they look like on the outer surface, but they'll go to the outer surface. Why? There's a simple answer staring you right in the face here. What is it that pushes them to the outer surface? What is it that pushes charge 2, electron 2, to the outer surface? Yep. Good. It's the Y component of F32. The Y component of F32 pushes it to the outer surface. And you can imagine if we did that analysis on the other charges, we'd get something similar. So they do get pushed to the outer surface. Now, let's take a look at F12 and the X component of F32. Which one's bigger? F12 that pushes it out towards the tip, and then F32, the X component right here, that pulls it back in away from the tip. Which one's bigger? Mark? F12. So what's going to happen to that electron as a result of those two forces? It's going to get pushed as a result of Y to the outer surface. It's going to get pushed as a result of F12 towards the tip. At some point, those two forces will end up balancing each other, the X component and F12. As we get further away from charge 1, F12 gets smaller, right? So at some point, they're going to balance out. And at that point, they're going to be in a state of static equilibrium. So everything's going to stop. What does the distribution end up looking like when they reach that point of static equilibrium? Well, the excess charges are on the outer surface, like you see in this third diagram here, and they're not evenly distributed now, but rather there's a higher concentration at the tip. Now, when you walk across the carpet and build up a charge in your body, and you go to shock somebody, what's the technique that you use to shock somebody? Okay, you're walking up, I'm going to shock Ryan here, okay? Let's pretend I'm on carpet and I got leather-soled shoes. Okay, walking across the carpet, building up a good charge in myself. What's the technique that I'm going to use to shock him? What do? Touch him with my finger. I don't do this, like touch him with the side of my arm. I don't do this, turn around and touch him with my back. I touch him with my finger. Why my finger? Sorry? Yeah, there's a higher concentration of electrons in my finger because my finger is, it's more pointy, right? You get a higher concentration of charge in pointy things than you do in flat or rounded things. That's why when we do the Van de Graaff generator, the hair tends to stand on end on good dry days because your hair is pointy. And you get a higher concentration of charge in your pointy hair. So if your hair all becomes this massive negative charge, they all end up repelling each other and stand up. Does that make sense? Pointy things get a higher concentration. That's why lightning rods on the top of buildings are pointy. Okay, they attract lightning more because they're pointing. The whole purpose of lightning rod is to attract lightning. We want lightning to strike the lightning rod. Why? Well, to prevent it from striking somewhere else on the building and causing a fire. Where does the lightning rod go, by the way? To the ground, right? It's literally a path, a nice, easy path for electrons to flow into the ground. And it's pointy because we can get a higher concentration of charge and cause electrons or cause lightning to strike there easier. Here's another one. Here's a hollow conducting object. This is real similar to that solid conducting sphere. It's a sphere, although it doesn't have to be a perfect sphere. The distribution of electrons ends up being the same, of course. They're going to get pushed away from each other. They're going to go to the, once again, the outer surface, and they're going to be evenly distributed. Notice 3 of the 4 diagrams, they're evenly distributed. In the one, they're not. When the shape is uniform, they're nice and evenly distributed. When the shape is a little more pointy, not so evenly distributed. But they always, the X-ray electrons always go to the outer surface, no matter what the shape is. The reason that I want to show you this diagram is not so much to show you the distribution, because it looks exactly as it did with the solid conducting sphere. But in this one, I want to show you the electric fields, not only outside, like you see in diagram B, but also inside. Let's redraw this just as a two-dimensional picture here. We've got an electron right here on the outer surface. We've got an electron right here on the outer surface, and an electron right here on the outer surface. Let's draw the field inside this hollow conducting sphere as a result of charge 1. Which way does it go? Okay, forget about outside. Okay, we know which way it goes there. Which way does it go inside? Left, right, up, down? As a result of charge 1, it goes, somebody said it? It goes up. It goes towards the negative, right? What about caused by charge 2? Which way does it go? Down and to the right. Goes towards it, right? What about caused by charge 3? Well, that's kind of a mess, eh? I'll tell you what, though. If you dealt with all 3 of these electric fields, or all 1,000 of these electric fields, if you had 1,000 charges, if you dealt with them vectorially and added them up vectorially, the x components and the y components, what do you think you'd get for the net electric field anywhere inside that sphere or that solid conducting object? What would the field strength be? 0. The field strength inside there is 0. That's a really, really important statement. There is no electric field inside the conductor. We call this a Faraday cage. This is why a car is a safe place to be in a lightning storm. Everybody thinks the car is a safe place to be in a lightning storm because of the rubber tires. Rubber is an insulator. It's a good insulator, but so is air. And the lightning was able to go from the cloud to the car through the air, so why wouldn't it be able to go from the car to the ground through an inch of rubber? Of course it can. Lightning will absolutely strike cars. Cars are made out of metal. Lightning will strike it. Lightning will strike airplanes. Happens all the time. Lightning strikes airplanes. You may have been in an airplane that was struck by lightning and not even know it. You are perfectly safe inside an airplane or a car that's been struck by lightning because the net electric field inside the car or the airplane is 0. And the reason it's 0 is because it all cancels out as a result of the distribution of charge on the outer surface. If there's no electric field, you can't be hurt, right? You can't be affected by electricity if there's no electric field. Does that make sense? Yeah?
Does the speed of the electrons distributing along the surface come into effect in that kind of thing? Because if lightning strikes the top of a plane or a car, it's back around.
No. Yeah, no. The net electric field inside, now if the vector analysis would become, the vector analysis here would not be fun, but the vector analysis there would be much, much more difficult. But the net electric field would still be 0. What ends up happening is that when a car gets struck by lightning, we say the charges get evenly distributed. They don't really, first of all, because the car is not a nice, perfect sphere, right? There's some pointy things on the car, although they tend to be rounded, but it's not a perfectly even distribution. In addition to that, they don't actually reach that point of static equilibrium in a car because as the lightning strikes it, the electrons builds up too much and they end up going around the car and discharging to the ground. So it changes, the distribution changes constantly on a car when it gets struck by lightning. But the net electric field inside, regardless of, immediately after it gets struck or 2 seconds after it gets struck or anywhere in between, the net electric field inside would still be 0. that make sense? So this term Faraday cage describes that situation of something that's enclosed in metal that prevents a net electric field inside. I've often thought of trying this, but never quite had the courage to do this. I've often thought of making an aluminum foil costume, like coating myself in aluminum foil and then walking up and touching the Van de Graaff generator to see if I avoid the shock. Because I should, right? Because the net electric field inside that conductor should be 0. It should conduct on the outer surface of the aluminum foil, through the aluminum foil to the ground, and not affect me. I just don't want to be the guy that tries it. That's all. We're going to give you a few questions to work on from check and reflect questions. You can work on them for the rest of class and then for homework tonight as well. Remember, there is going to be a practice question set go up as well. The questions that I want you to work on, page 569 are up on the board here right now.